This lesson is going to be focused on the Pythagorean Theorem. Listed below are the three main Pythagorean Theorem Common Core standards for Common Core states. Most states still teach Pythagorean Theorem, and they teach exactly this information. They just call it something different than a Common Core standard. However, here are the Common Core codes if you are in a Common Core state. And the first one is 8 for 8th grade, G for geometry, and then B.6, which is to explain a proof of a Pythagorean theorem and its converse. And the next one, 8.G.B.7, is to apply the Pythagorean theorem to determine unknown side lengths in right triangles in real world and mathematical problems in 2 and 3 dimensions. And finally, 8.G.B.8, which is to apply the Pythagorean theorem to find the distance between 2 points in a coordinate system. We won't be focusing on 8.G.B.8 in this lesson, as it does incorporate coordinate grid, and you could use the distance formula instead of Pythagorean theorem, but they're kind of interchangeable because they're very parallel and related in their construct. Okay, so we're going to dive right into 8.G.B.6, which is the ability to explain a proof of the Pythagorean theorem and its converse. And this brings in conceptual lens and the idea of understanding the concept behind Pythagorean theorem, not just a squared plus b squared equals c squared, but why does a squared plus b squared equal c squared? And the picture on the left is a diagram I created for my students digitally in class one day, and it really truly visually shows it. Normally I like to have students actually do this with grid paper or with blocks, Unifix blocks, to see that it actually does work. So first we need to understand the definitions behind the parts of a right triangle. Pythagorean theorem only works for right triangles, and so you don't want to try to apply it to an isosceles triangle or an equilateral triangle or a scaling triangle unless that isosceles or equilateral are also right triangles. The right triangle is any triangle with one right angle, and we always show that with a small square in the corner displaying that right angle. A right angle is an angle with a measure of 90 degrees exactly, not 91, not 89, but 90 exactly. If that square is not visually shown in geometry, you actually get to prove that the triangle is a right triangle through measurements. But also in 8th grade math, you can use the Pythagorean theorem to test whether or not that angle must be a 90-degree angle, and you can do that by using the Pythagorean theorem. The legs are either of two line segments that form the right angle of the right triangle. So this is going to be your A and your B. Those are your legs. The hypotenuse is the longest side of the right triangle, and that's your C. Remember, it's the longest side of the triangle, and that's important because some test questions will ask which side of a triangle in a right triangle is the hypotenuse, and if they give you 3, 4, 5, no matter what order it is, you would know 5 is the hypotenuse because of the fact that it is the longest side of a right triangle. The hypotenuse is also opposite of the right angle, so you should be able to draw a diagonal line from that right angle across to find your hypotenuse. Okay, so we're going to go back to that first slide and display the illustration I first started with to explain the proof of the Pythagorean theorem and its converse. So we can see that there's a triangle in between all those squares, and we can see that there's blocks that make a length of 3 across the base. If we can see within there, we can actually look and notice that there's actually a total of 9 units going out from there. Well, a square with a 3-side length would mean that the other sides are 3, and therefore the area of that square is 9. Going out the other direction, we can see that this side is going to be 4. And if we build a square out from that direction, it has to be 4 rows and 4 columns. And now we can see that that square would have to have an area of 16. Based on a square, meaning a square that has a side length of 3, and b squared, a square that has a side length of 4 squared, we should be able to figure out what c squared is. And that's what the Pythagorean theorem is. So 9 plus 16 equals 25. Now remember that that's the measurement of c squared, not c itself. So if you use grid paper and you actually cut out pieces or you use Unifix cubes, you can actually line them up to determine that the square going this direction would actually have 1, 2, 3, 4, 5, and it's going to have 5 rows and 5 columns going out the other direction, showing an area of 25, which would match the fact that 9 squared, or 9 plus 16 does equal 25. But what is our side length? Remember, it's the square root of that, so we're finding just one number here. And so we see it as c squared equals 25. That means c has to equal 5 because it's c times c. Okay, here I've got a clean version of that same triangle. So we're actually going to go just straight through the Pythagorean theorem. We've proven it by using the building of a square off of each side length, seeing the area of that square. If it has the same side measurement, it must be an area of 9, it must be an area of 16, etc. But now we're going to actually walk through the Pythagorean theorem. And the Pythagorean theorem states that for any right triangle, a squared plus b squared must equal c squared. So that's our Pythagorean theorem. It's something students have to memorize and understand what to substitute in for those values. So a could be either side because with addition, it does not matter what order you add things. 1 plus 4 is the same as 4 plus 1. So we don't want you to worry about which side's A and which side's B. We just want you to know that it is a leg. So we're going to start with 3. And we'll enter that in, 3 squared. Then our next leg is b. So with that being our b squared, we're going to swap that out and do our 4. And then lastly, we're trying to find c. So that's c squared. Now, following the order of the operations, we would do exponents first. So 3 times 3 is 9, not 3 times 2, 3 times 3. Remember that little 2 means to multiply itself twice. Okay? So we have 3 times 3 is 9, and then we're going to have 4 times 4, and that's 16. And we know that that equals c squared. So our value is 25. That equals c squared. What we want to show at that point is that we know c equals the square root of 25. And that brings in the previous lesson that we were talking about with square roots and cube roots and showing how square roots do come into use in Pythagorean theorem very much so. And c therefore equals 5 because 5 times 5 is 25. And the square root of 25 is the number times itself to equal the sum that's within the radical symbol. Okay, now we're going to solve the next triangle. Again, we're missing the hypotenuse c, so we're going to use a squared plus b squared equals c squared to determine c, the hypotenuse of a right triangle. So let's start with our legs. These are our legs. Okay, we've got a squared, which is 6 squared. And then we have our other leg, 8, and that's going to be 8 squared. and that's going to equal our c squared. So this time I'm going to write it out fully so that students or people watching see it step by step. This is 6 times 6. This is 8 times 8. And that's going to equal our c squared. Okay, so now we can solve the multiplication, which is why exponents need to be done first. It needs to be noted that that 6 times 6 is by itself. It needs to happen initially. So here we have 6 times 6, and that's going to give us our 36. And then we have 8 times 8, and that gives us 64. The solution to that addition problem is going to be c squared. So now we do addition. 36 plus 64 is going to equal 100. And that equals c squared. Remembering that c squared is c times c. So we're really looking for what is the square root of 100. And the square root of 100 is 10. 10 times 10 is 100. And therefore c equals 10. When learning about right triangles in the Pythagorean theorem, we also learned about Pythagorean triples. And Pythagorean triples are 3 positive integers that make up a right triangle. And a very commonly known one is the 3, 4, 5 right triangle. Now what's interesting is if you can memorize 3, 4, 5 as being a Pythagorean triple and being a right triangle, you can actually think about using scale factor to find similar figures that would immediately also be right triangles in Pythagorean triples. So for example, 3 times 2 is 6, and 4 times 2 is 8, and 5 times 2 is 10, and we now see, oh, look, there's our other triangle that we just solved. So I used a scale factor of 2 on each of those side lengths to find that next Pythagorean triple. But that's another concept that is taught when learning about Pythagorean theorem and right triangles. It is very possible to have an isosceles right triangle. An isosceles is a triangle with 2 sides that are congruent. In this case, we see that our side lengths are 5 and 5. Those are both our legs, and we're trying to find c. So we would use the Pythagorean theorem, a squared plus b squared equals c squared to solve this. And we substitute in our values. So we have 5 squared plus 5 squared equals c squared. 5 times 5 is 25. Our other leg is also going to have a 25 area. And that's c squared. When we add the two together, we get 50, and that equals c squared. So c must equal the square root of 50. But what do we know about the square root of 50? It's not a perfect square. 7 times 7 is 49, and 8 times 8 is 64. But 50 is not going to be a perfect square. So in a previous lesson, when I taught about square roots and cube roots, we learned how to estimate square roots. We know that the square root of 49 equals 7, and the square root of 64 equals 8. And we know that this is a lot closer than it is to 8 because it's the square root of 50. So we know it's going to be close to that. When we type it into a calculator, we are going to get an irrational number. It is going to be approximately 7.071, and it kind of goes on forever because it's irrational. So you can't really state exactly where it is, but you could estimate the side length of that hypotenuse. Okay, now we're going to solve for when we are missing a leg instead of the hypotenuse. So we still use Pythagorean theorem to do this. We also bring in a lot of algebraic reasoning. So a squared plus b squared equals c squared. So our leg, we have 12 squared, but our other leg we're not sure about, so it's b squared, and that equals our hypotenuse, 20 squared. Okay, so we substituted in the values for the information given in this triangle. And now we want to follow exponents and complete those. So 12 times 12 is going to be 144. And 20 times 20 is 400. Then to solve algebraically, we know that we need to do the opposite operation that is currently present. While there isn't an addition sign in front of that 144, it is a positive 144, so the opposite would be to subtract 144 from both sides of the equation. That's going to zero out the one side, and when we subtract 144 from 400, we get 256. We haven't done anything with that b squared, so we have to bring it down. So now we can see all we have to do is find the square root of 256 to figure out what 1b, or the side length, is. And the square root of 256 is 16. We can go back and check our work by substituting all of the values back in and have 12 squared plus 16 squared, and what does that equal? So we have 144 plus 256, and when we add those together, we get 400, which we found to be 220 squared. Okay, the converse of the Pythagorean theorem is basically taking the Pythagorean theorem, and rather than finding the missing side length, you're given 3 side lengths and you have to determine, is it a right triangle? So for example, if I'm given the side lengths 5, 12, and 13, is that a right triangle? If we first go back to our terminology, we know that the longest side has to be the hypotenuse. Sorry, my writing's a little bit messy right now. There we go. So we can substitute that in to see if it works. A squared plus b squared, does it equal c squared? So 5 squared plus 12 squared. The question is, does it equal 13 squared? So first we do 5 times 5 to get 25. Then we do 12 times 12 and we get 144. And finally, 13 times 13 is 169. So we then take our addition, 144 plus 25. It does equal 169. And so yes, this is a right triangle. This concludes our overview on the Pythagorean theorem. For additional practice, there are multiple websites out there. Many of these have the key with them, so you can do the work and then check your work afterwards. Here are a couple that I've used in the past for some worksheets. I've also created my own practice ones, but for your use, especially during this time where many of you are at home trying to figure out how to homeschool your kid or teach your kid concepts, these websites are very helpful.